Alright, today we're going to be talking about rotational motion. First of all, let's focus in on circular motion. Circular motion is all things that are moving in a circle. We've talked about linear motion as being objects that are moving along in a straight line, and we can determine the velocity or speed of linear motion by determining the distance traveled and how much time it takes. When an object is traveling in a circle, we also need to take a look at what is changing. Even if the linear speed is not changing, because our direction is constantly changing, we say that uniform circular motion has a constant acceleration, and that constant acceleration is what is causing it to turn. Now, here are some quick questions for you. Which parts on a merry-go-round move the faster? Those near the outer edge or those near the inner edge? In order to answer that, you have to think about two different things. What kind of faster are you talking about? Are you talking about linear? Or are you talking about rotational? If you are talking about linear, the ones on the farthest side have a much further distance to go in the same amount of time as the ones on the inner side have to travel. So, if we're talking about linear motion on a object moving in a circle, the ones on the outside are going to be moving fastest, and the ones on the inside are going to be moving slowest, and the ones at the very, very center will be moving the slowest of all. But if we're talking about rotational speed, then all points are the same, because all of these points must complete the circle in the same amount of time. So they will complete the same rotations per unit of time, even though at each point they may have to travel linearly further. In order to calculate this, recognize that rotation is revolutions per unit of time. And another way we've oftentimes expressed that is through frequency, and that is measured in cycles per second. Linear motion is taking into account how far they have traveled, so the distance divided by the time. The distance can be calculated by multiplying the number of revolutions by the circumference of our circle, divided by the amount of time it took to complete that. Now, inertia is an important concept. Remember, inertia is the resistance of an object to change. Rotational inertia is the resistance of an object to turn. The law of inertia for rotating systems is as follows. An object rotating about an axis tends to remain rotating about this axis at the same rate about the same axis unless interfered with by some external influence. So I want you to think about how this would apply to bullets, arrows, and even the earth. So an object rotating about an axis tends to remain rotating about that same axis unless interfered with by some external influence. So, how do we calculate that? We need to figure out the moment of inertia. This is the rotational inertia, how hard it is to begin things moving in a circular motion, or how hard it is to stop. This sluggishness of an object is its rotational inertia. Now, the distribution of mass is key. Why is it that when you have a tightrope walker walking on a tightrope, that they carry this long mass with them? Well, when they increase or they spread out the mass across a greater area, they increase their rotational inertia. It makes them more stable. It gives them more rotational inertia, meaning that it takes more energy to cause them to turn. So, the spreading out of mass is key for developing rotational inertia. So that being said, if I have a hollow cylinder and a solid cylinder, which is going to have the greater rotational inertia. The one that has the mass spread out is going to have the greater rotational inertia. What forces cause things to go in circles? Well, one of the things that causes things to move in circles is torque. Just like impulse will change momentum, torque will change rotational movement. This is basically rotational versions of force. So torques change the rotational state of a motion. It will start it turning, it will stop it from turning, or it will cause it to turn faster or slower. Now, the equation that we use to help us figure this out is that the force is equal, or the torque is equal to the force multiplied the lever arm length. Now, this is hugely important and is very applicable in your everyday life. Now, this is a vector, meaning direction matters, and it's measured in Newton meters or foot-pounds. Let's take a look at an example. Now, if we were to just look at 1/2 of this seesaw situation, we can start taking a look and understanding the concept of torque better. The amount of torque that is being placed on this lever arm is equal to the amount of force, the mass of our donkey, multiplied by the length of our lever arm, or the distance between the fulcrum and the end. So, this would give us torque. Now, if we look at the other half of our scenario, we can see that we can have equivalent amounts of torque even with very, very different amounts of force. If we increase the length of this lever arm, the mass of this baby is enough to overcome the mass of this big, heavy donkey. Aristotle once said, "Give me a lever and I can move the world." He was referring to this very idea, that it only takes a small amount of force if you have a long enough lever arm. Let's look at this mathematically. Let's say we have 150 pounds multiplied by 2 feet. This is going to give us 300 foot-pounds. Now, how far away on this other side would we need to place a 50-pound block so that we could also end up with 300 foot-pounds? Well, we have 50-pound block, and we need to multiply it by x. By setting these two equations equal to each other, then dividing both sides by 50, we come up that we would need to move our block 6 feet further down the arm in order to get equivalent amounts of torque. Here's another way of looking at it, and an important one. If we wanted to increase the likelihood of loosening up this bolt, what would we need to do? Well, we have a couple of choices. We could increase the amount of force that we are applying here, and that would certainly help. However, we would not need to increase the force so much if we increase the length of the lever arm. That increasing the length of the lever arm along the line of action, not at an angle, would provide for us the best amount of torque. Let's move on. I want to talk about the center of mass and center of gravity. Now, the center of mass is the average position of all of the mass. If we were to take a meter stick and were to measure it down, measure it down, measure it down, measure it down, we would find a point where half the mass was on one side and half the mass was on the other. This would be the average position of the mass. This can also be found on not straight linear, but in global objects. Now, the center of gravity is slightly different, but usually is used interchangeably. This is the average position of weight. Remember, the difference between mass and weight is that mass is simply a measurement of how much stuff is in something, whereas weight is a measure of how much that stuff is affected by gravity. One of the more interesting things when we look at the center of mass of rotating objects is that that center of mass will behave as though it were a single point object. If we were to take a hammer and toss it through the air, while the hammer itself may go flying over end, the center of mass would behave as if it were a single object. If we were to take all of this mass and crush it up into a single ball and provide the same amount of force, it would follow the same line through the air. Or, if we were to spin it across the table, that center of mass would be following a straight line if there are no other external forces acting on it. Now, how do you find the center of gravity? Well, there are a number of ways in which we can do that. The center of gravity can be found by, well, one way is you could take an object, suspend a string with a plumb line, and wherever that string drops down will naturally be over the center of mass. So if we change the position of our object and we drop our plumb line down again, where those two lines cross will be the center of mass. Now this can hold true even if the center is actually outside the object. For example, in this donut, if we used our plumb line and dropped it down, drew a line there, changed its position, dropped the plumb line, we would find that the center of mass is actually in the middle. Now this can be very, very important when we are studying athletes who are doing high jumps and pole vaulting, because their center of mass is not necessarily still as they change their body shape going through the air, located inside their body. Let's talk for just a moment about equilibrium. Remember, equilibrium exists when all forces, the sum of all forces acting on an object, are zero. Now, equilibrium can exist in three different forms. We have stable equilibrium, we have unstable equilibrium, and neutral equilibrium. If an object is in stable equilibrium and it is displaced slightly and released, the object will simply return to its old position. For example, if we had a ball in this bowl and were to put a force on it by this finger and displace it, the ball would go up and then it would naturally go back down to its lowest energy level. This would be stable equilibrium. Another example might be found if you looked at a triangle shape. If I were to displace the triangle, tipping it up a little bit, and release that force, it would naturally come back down to its most stable, lowered position. Now, another example of equilibrium is unstable. That would be an example if I were to place the ball on top of the bowl. If I displace it slightly from equilibrium, it will not return to its original position. In fact, it will fall down and find a new lower energy position. And there is no amount of wishing that will cause it to automatically come back up to its unstable position. Another example might be the triangle turned upside down. I could get it to balance like this, but if I displace it even a slight little bit, it's going to fall off of that balanced position and not come back up again naturally. Neutral equilibrium exists when an object is displaced slightly and the center of gravity or center of mass remains where it is. For example, this ball on the table, if we displace it, the center of mass neither raises nor lowers, just simply remains where it was. Now, what is the force that causes an object to go around in a circle? We call this force centripetal force, and it is a center-seeking force. Remember, Newton's first law of motion says that an object in motion will stay in motion in a straight line and at a constant speed. So if it is not staying in a straight line and at a constant speed, but instead it is changing its direction to follow a circular path, there must be a force acting on it. That force is centripetal force, meaning center-seeking force. Let me give you some examples. If I were to take a tin can and a string, holding on to one part of the string and whirling the tin can, The string would be providing a tension force that would cause the tin can to not go in a straight line at a constant speed, but instead to whirl around. The moon and the earth is another example. This is where the force of gravity provides that centripetal force, where the moon is then going around the earth. A car on a circular path. The force of friction, or the normal force, would actually at the same time be causing the car to turn around corners and not continue on a straight line path. Now, there is an opposite pseudo-force. A pseudo-force means fake force, called centrifugal force. This is called a center-fleeing force, and it is not real, because forces can only occur in pairs, and the centrifugal force depends entirely on your frame of reference. The only time the centrifugal force is identified is if you are actually in a rotating frame of reference. Some examples would be when you are going around a corner in a car and you feel yourself pulled to the outside edge. Now, in truth, that's what it feels like, but in reality, your body is just simply trying to go forward and keep moving in a straight line at a constant speed. The car is changing, which makes it feel as though you are being pulled to the outside edge. So, in truth, the centrifugal force is really just an effect of Newton's first law. However, just because it's not a real force does not mean that if you are in that rotating frame of reference, it has no effect. When you are experiencing the centrifugal force, you are in a frame of reference, it actually influences our view of nature. For example, we actually use this centrifugal force when we're simulating gravity in a free fall environment. Here's an example. In order for us to get simulated gravity, we would need to be spinning our satellite or a space station at a certain speed. If we are doing this we are providing it with a centripetal force and torque, which is causing it to turn. However, for the guy who is running on the inside, it feels as though he is being pulled down towards the bottom. Now, where would you experience the greatest amount of centrifugal force? Right here along the edge, where you're the furthest away from that center frame of reference. Now, how much force of gravity or simulated gravity would you experience right at the middle? Well, you wouldn't experience any, because remember, it's an effect of Newton's first law of motion. So the further away you are, the further distance you're having to travel, the greater your linear speed, the greater that feeling of a gravity that you will experience. Now here's a question for you. I'm not going to give you the answer because I want you to think about it. What effect would it have if you were to be jogging inside the space station and you were jogging in the direction of this turn versus if you were jogging opposite the direction of the turn? Would there be an effect of the simulated gravity? Remembering that it is due to this rotational speed that you're experiencing any gravity at all. Okay, conservation of angular momentum. Just like energy is conserved, just like matter is conserved, angular momentum is also conserved. If there are no external torques acting on a rotating system, then the angular momentum is conserved. This means that the final angular momentum is equal to the initial angular momentum, just like when we were looking at conservation of linear momentum. Okay, here's some quick review questions. In walking, people normally bend their knees. Why? Please read these questions and tell me an answer. Now, if you want to move more smoothly, would you want to increase your rotational inertia or lower your rotational inertia? Remember, an inertia is your resistance to changes in rotation. Bending lowers the rotational inertia, because it doesn't spread out the mass further and makes it easier to use your legs. Which is harder to stop? A rotating rod with its mass predominantly at the middle of the rod, or with its mass predominantly at the ends of the rod? Or is it neither of the above? You're looking for which is harder to stop. What do you think? If you chose at the ends of the rod, you're correct, because by spreading those mass out, you increase the rotational momentum, which means once you get this moving, it would be much harder to stop than if you were looking at the ones where the mass is just here in the middle. A ball is at rest on a horizontal table. It's in a state of what kind of equilibrium? A ball is at rest on a horizontal table. Go ahead and answer. If you chose neutral equilibrium, you're absolutely correct. Now, if our ball was at rest on the top of a curved bowl, which would it be? Correct. Unstable. And if it was at the bottom of a curved bowl, which would it be? It would be stable. Which of the following forces is a pseudo force? Remember, pseudo meaning fake. Is tension on a rope a pseudo force? No, we certainly can experience it. If I pull on the rope pulls on me, so it is a real force. The force of gravity? Nope, once again, that is a real force. I pull on the earth pulls on me. The force comes in pairs. A centripetal? Nope, once again real. It comes in pairs. The moon pulls on the earth pulls on the moon. Friction? Once again, it's a real force. It is countering motion, and it has to do with the contact surfaces between two objects. Centrifugal is the only one that only exists in a single frame of reference. It only exists when the frame of reference is rotating. And it really is just an effect of Newton's first law. All right, I hope this helped.